Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi everyone. We might as well go ahead and get started. But before we jump into this next talk, I've been asked to give a couple of announcements. For starters, the session abstracts and speaker biographies are now online on our website. Are we on now? Yeah. Thank you. Thank you. So again, two announcements. One is that the speaker biographies and the talk abstracts are now online on our website. And second, many of you probably already know, for those of you who are attending and who are faculty, we will be giving out access to Azure for sample development and whatnot. If you've already registered through the website, you have access to this and instructions on how to get it. If you registered in the last week manually, after the registration site was closed, please see somebody out at the desk and they'll get you on the list of people who can get access to Azure for evaluation purposes. Okay. In the next 90 minutes, we'll be telling you about Azure for Research. My name is Roger Barga. My colleague Jared Jackson will be presenting with me. And other contributors to this talk include Nelson Araujo, Dennis Gannon, and Wei Lu. Our team is responsible for actually working with external researchers, developing services, providing data sets for Azure for Research. So our day job is really working with researchers to leverage our cloud computing platform to advance research. We are the new kids on the block. Hopefully you heard earlier today, you heard the talk from Deepak on Amazon and also heard about Google. But relatively speaking, our cloud platform is still in its formative stages, been released less than a year. So we're going to spend a fair bit of time, in fact, the first 35 minutes talking about Windows Azure, just giving an overview of what it is, because we'd like you to leave today having an understanding of how our platform as a service is differentiated from infrastructure as a service and where it's trending. We'll also talk a little bit about Microsoft and cloud computing, how we see cloud computing, not definitions, but the kind of investments we're making. Then I'm going to turn it over to Jared, who's actually going to talk about research applications that we have built on Azure, actually run some demos of real code running on Azure for some of the research services our team is starting to build, and then drop down and actually talk about how they're built and a closer technical look at Azure. And then we're going to close by talking about our Cloud Research Engagement Initiative, which is where our group is offering access to Azure to researchers through government funding agencies. And it's an international program, so I'll tell you about what we're doing with the NSF and what our team is offering. But again, this is just part of an international program which is going to be extended to countries around the world. So let's jump in. Microsoft and cloud computing. Clearly, if you haven't gotten the sense from the talks today, computing and science are tightly coupled. In fact, we're making a scientific infrastructure and a society that's tightly coupled with computing infrastructure. And if you look at the major advances that have taken place over the last 10, 15 years, you see that science and computing power are really tightly coupled. So you can't help but ask yourself the question, with the advances that are taking place in cloud computing, multi-core computing, and even potentially in the future quantum computing, what will the future of research look like? And this is an area in which Microsoft is investing heavily to try to understand and actually play an active role in that. And of course, the Fourth Paradigm book has been mentioned several times, in which people are looking at envisioning what that future looks like. But the missing chapters of that book is, what are the technology solutions that actually deliver those visions of those authors? So I think this is an active area for us to be involved in. And a slide that Dan Reed uses a lot in his presentations, which I happen to like, talks about the Sapir-Whorf hypothesis. And that is, an individual person's thinking and their ability to reason is actually a function of the language they have. And we can actually see analogs in scientific computing. The tools that you have to compute, the amount of data that you can manipulate, changes research, has an impact on the kind of research questions that you can ask and how you go about asking these questions. And again, we see many examples today in multi-core sensors, ubiquitous sensors, clouds, cloud services. You can say, what lessons can we draw? And what are probably going to be the big macro influencers on this space? And you can't help but acknowledge the pull of economics, which we think, even though you may have heard some wonderful talks today about clouds, very little talk about the economics. And if you look at how economics has shaped how we've leveraged technology, Moore's law really favored, consumer commodities, commodity hardware. And economics drove enormous improvements in commodity hardware. And specialized mainframes and clusters faltered. No matter how superior they were, because of the economic draw of getting commodity hardware, easily deployed, very cheap to deploy, we changed our algorithms and we changed the way we conducted our research to take advantage of this economic trend. And today's economic drivers, many-core, multi-core processors, accelerators, cloud computing. And so this really is going to drive change. You may have a better algorithm that works on an MPI cluster today, but as cloud computing has an economic advantage, you're going to see researchers start to think about how to leverage that platform to carry out the research. And in the process of doing so, be able to ask different questions. And just, for scale, this is a paper, this is very dated information from a Lattice paper that James Hamilton and others published that talked about economies of scale. Both, and what you're seeing here in this column is the cost for a small-sized data center for networking, for storage, and for administration costs. And this is the costs for a large-scale data center, our Hotmail services, or MSN, excuse me, and the actual cost and the ratio of the cost, this cost savings. Those are incredible, ratios of improvement in our data centers. And the real killer here is administration, where an individual admin may only be able to administer 140 machines on a mid-sized data center that you might find at a university. But at cloud scale, we're trending well over 1,000 servers or more per person, effectively reducing that high overhead. And just as a matter of scale, this is just one of our data centers. A single one of those is 11.5 times the size of a football field. Patterson was talking earlier today about how many servers could potentially fit in one of these facilities. And if you add up the raw compute, the raw disk, the raw memory in any one of those facilities, it's actually greater than all of that you'd find in our Department of Energy facilities for doing research, which is what we think of as our technical computing backbone in our country. So the size of the scale and the economics of these things is truly staggering. And we've seen this picture before, the nice angled parking for the containers to back in. And what they're really connecting to are these units in blue in the lower right-hand corner that bring power, cooling, and networking to any one of these containers. And the beauty of this is that within a few hours, certainly within a day of backing up a container, all of the servers in that container, 2,500 to 5,000, are up and running and part of the compute fabric in just one day. So just the ability to deploy that many services is really quite striking. And what people might not appreciate is just how fast this is unfolding. Microsoft is already in its third generation of data center design, which is the Chicago facility with the containers. We're doing away with a lot of the computer room air conditioned controlled. We've now gone to containers with just a concrete shell, but we're actually driving and pioneering even more changes. This is Christian Bellotti in his data center in a tent, where they're actually moving data centers out into the ambient temperatures and running them without the cooling to try to bring the PUE, or the power utilization efficiency, closer to 1. You're not paying to cool the room. You're actually trying to have a wider operational range. This is Rick Rashid. It's not a very good picture, but standing in front of a cluster made up of Atom processors, very low energy processors to make up a rack. And our fourth generation, a mock-up of our fourth generation data center, we're even doing away with the $200 or $300 million container, and we're just simply putting, or the shell, if you will, of the building, and just putting the containers themselves out and stacking them without any shell around them, and actually selectively putting backup systems or batteries on per containers to back them up, so we don't have the large diesel generators. This will drive even more economies of scale, even more savings through the data center. So it's going to be an area of rapid innovation and improved cost savings over time. But enough of that. If you're to walk around in one of these data centers, and we're going to be talking about benchmarks and performance, but if you were to walk around one of these data centers, you might say, what's really different about one of these facilities relative to the cluster I'm familiar with, or the data center that we have at our university? So we can just pick a few things to contrast. I've picked up node and system architectures, the communication fabrics, the storage systems, reliability and resilience, and then we'll transition into programming models and talk about Azure. First off, if you look at the node and systems architecture in a data center relative to a cluster, there really is very little differentiating factors between them. They're Intel Nehalem processors, AMD Barcelona or Shanghai. There are multiple processors per node, per rack, a big chunk of memory on the nodes, so they're actually indistinguishable at that level, at the processor level. Where things start to get really interesting is the communication fabric. On an HPC cluster, This is actually a graph of the top 500. What you're seeing is over time on the top 500 systems, what have they used for the technology? And I realize this isn't easy to see, but you can actually download the slides. What we're seeing is basically, the Cray interconnect, gigabit Ethernet, InfiniBand over time. This is what you're going to find in a high-performance computing cluster. The bisectional bandwidth is great, and you almost have a very flat network, so the communication from point to point is the same across the entire cluster, and everybody can talk to everybody. Hence, programming models like MPI work very well. Every node can take a little bit of work, do a little bit of computation, share its states with others, and they can continue to march down and to perform the processing. But it's quite a bit different in a data center. In a data center, we might have a rack of 20 to 40, and that number is increasing rapidly, processors. At the top of the rack, we'll find a top-of-rack switch, which is gig E. And then at the second level, we actually see a 10 gig E, but it's actually just partitioned heavily. And in fact, there's a lot of oversubscription taking place on this network, such that if all of the machines try to talk to each other at a very fine granularity, the latency is going to be high, the collisions are going to be high. So there's a lot of oversubscription on these networks. And even at the next layer, at layer 2 and layer 3, you have continued oversubscription rates, such that point-to-point communication is no longer possible in these systems. Instead, you want to pull off a large piece of work and work for a large period of time before you have to get off that node and exchange information. Because again, if you're not under the same top-of-rack switch, the communication penalties are going to be high, which is why during some of the questions today, people are asking about MPI codes. This is one factor why they don't simply work well unless you're coincidentally trying to get everything under the same rack. And we actually try not to, as you're going to see later, get them under the same rack for reliability purposes. So huge differences in the communication fabric. But again, we're coding around that to take advantage of commodity switches, commodity routers, etc. And second, storage systems. In HPC, you might have a local scratch per node, but it's for most part non-existent local storage per node. Instead, you have your secondary storage as a SAN or distributed file system, and you have petabytes of secondary storage. In contrast, in a data center, much like a lot of the Google infrastructure you've been hearing about, you have terabyte local storage per compute node, which makes for great local storage if you want to bring a large piece of data over to work with. And your secondary storage is just a bunch of disks. And yes, there's going to be eventual consistency and replication, but again, you're not going to see any SANs in these. And tertiary storage is absolutely non-existent. You have no big tape backup. You have no ability to do checkpoints. And moving on, reliability and resilience. In HPC, especially if you look at the trends over time, they do periodic checkpoints because something is going to fail. And most of the codes are fairly fragile. If something fails, you roll back to your last known good checkpoint, reinstall it, and continue on. But over time, as we've gotten more and more compute nodes, the mean time between failure for something failing, even when you're trying to boot the machine up, has been approaching 0. And checkpointing frequency has been increasing. And the I/O overheads, the amount of time to do a checkpointing is going up from 20 to 30 to 40 minutes to do these checkpoints. They're simply not scaling. In a data center, everything's loosely consistent. Ken Berman, of course, would like to convince us otherwise in his talk. He had a great talk. But the system is actually designed to recover from failures automatically. Failures are going to happen, and the system is instead designed to actually pick up from failure and resume computation. So very different models for resiliency and reliability. And then finally, programming models and services, which is going to lead us into what we're talking about in our talk today about Azure. And this is kind of an extension of what David Patterson was talking about. Is you really see that cloud programming models and the systems that they support is a spectrum today. With discrete points we can point out like Amazon Web Services. Your VMs look very much like the hardware you have today. There's no limit on your application model. User must implement, and there's services to implement scalability and failover. At the other extreme, we have very highly constrained models, but a heck of a lot of automation for the verticals that they're targeting. And somewhere right here in the middle is Azure, which is our platform as a service. And that's what we'll be talking about today in our talk for the next 30 minutes. So let's start with Windows Azure and talk about a few fundamentals, and then talk about what kind of services it provides during runtime before looking at the demos. So we start with a bunch of machines in a data center. And yes, they're probably going to come in through a container that's been backed up to one of those power supplies I showed you earlier. We have something, and what differentiates Azure from other models is we have something called the Fabric Controller, which is highly available. It's a Paxos cluster, and The fabric controller owns all of the hardware inside of the data center. It actually burns the hardware in from the moment it's backed in. It actually knows the performance profile of an individual piece of hardware, be it a CPU, be it a piece of memory, a router, or a load balancer. It understands what its performance profile is, and it's going to monitor it. So the first thing it does is it installs an optimized hypervisor, and then it puts in a host virtual machine, which is Windows Server 2008. Then it installs a guest VM, which is where your code can run. And it can actually install 7 of them to be date, or 8 of them to be accurate, to run on an individual node. That's really a function of how many cores that you have available to you. And as you'll see, we can actually slice that up, a node, a unit of resource, computing resource, in various ways. We could, at a minimum, we could just give you one core and give you a slice of the CPU, which is a 1.5 to 1.7 gigahertz x64. We can give you your fair share of the memory, which right now is 1.7 gigabytes. Give you 100 plus megabits per second of the network. That's a core slice of the network. And local storage, which is, again, a fair slice, an equal slice of the amount of disks that you have available. Or you can say, I want a very large VM, in which case I want everything that's on that node. 8 cores, 14 gigabytes of memory, and 2 terabytes of local storage. And on top of that, we're going to be running .NET Framework, Windows Server, and Windows Server 2008 Enterprise Edition. That's the basics. But then we actually install the Azure platform. And this is where things start to differentiate from just being able to put up a VM, be it a Linux or a Windows 2008 with your code inside of it. Instead, we're saying, look, we want you to tell us what the requirements of your code is. We want you to fragment it up and just kind of give us some hints about what it's supposed to do. And we'll be talking about this in 2 pieces. One, the compute, and the second is at the storage. The Windows Compute Services, there's our Fabric controller and the Fabric you're running on, which is just all of the machines that you need access to. We differentiate your code by a web role or a worker role. Over time, we'll see more roles introducing, which is, again, your way of packaging up your code and saying how you want it deployed and how you want it to, what you want it to be able to do. Your web role is really what's going to be talking to your customers. It's where you're going to run ASP.NET, WCF, any code that's going to talk to the outside world. There's a load balancer that will be stuck in front of that. So if you actually have a very large web presence, you want to support thousands of users, you're going to have multiple copies of these web roles to actually interact with the outside world with a load balancer sitting in front of it that people can send HTTP requests to. The back end is where the work gets done, the worker roles. That's where the mainline code goes. Standing between these, there's actually something called an agent, which we can talk about in the Q&A, but that's what's monitoring the health of your installation, your code that's running on the VM, and sending that back to the Fabric controller to let it know how things are running. It's monitoring the hardware, and it's monitoring your software. And this is where we'll throw in the pretty pictures of the queues. Let me just go ahead and just stretch this out. So works come in through the web role. The first thing it's going to do is actually bundle the work up. It actually could partition the work up and break it up into multiple units. You may have given it a large chunk of work to do, and what your web role may do is actually tease that apart into multiple chunks. Each one of those chunks would actually go into a separate queue request. This is work to be done. You'd actually have a farm of worker roles monitoring that queue, looking for work to do, and the moment a piece of work appears in the queue, they'll pull it off and actually start executing the queue. And again, because they're separate, because they're different instances that are running, you can scale out the 2 independently, determine how compute intensive your work is or how chatty your external interface is. In fact, you can even take it out to a large extent, and you could actually partition even your mainline code up into multiple stages, sticking queues in between it, because you may have a step in your pipeline that's very compute intensive, and you can partition the work out. You'll have tens of workers actually doing that, divide and conquer of the work. Then you might have the actual piece of work to actually glue all those results back together to actually make a complete result for the user. And you'll see that in some of the demo applications we show you later. But again, you have durable queues standing in between them. The queues help you decouple the parts of the application so you can scale it independently. It's for resource allocation. You could even have different priorities of users. High priority paying customer, you're going to have 100 workers responding to their requests. A freebie service, you may have just 1 worker actually responding to it. So again, you can break your work apart into different patterns and assign them different workers and glue things together with queues. And it masks failures. Again, we're going to assume that failures are going to happen either due to your own code or simply we're moving workers around across the data center. You have to design for failure. The idea is if a worker picks up a piece of work out of a queue, this is a durable queue. the item really didn't get deleted until the work gets completed. If this worker were to have failed, the item will reappear after a specified period of time back in the queue, and some other idle worker can pick that back up and resume computation against that piece of work. So again, it can mask failures in our system. And more recently, we even have TCP, we have IP connections between individual workers. You don't have to go through queues. As you might imagine, a durable queue actually is a very expensive write operation to make. The overheads are high. If these workers needed to actually exchange information, we now have point-to-point communications, but again, it's not durable, so you're exposing yourself. Should something fail, you're going to lose that work. Okay, so moving on to storage. There's actually one element missing here, but we're not talking today about SQL Azure. We're just looking at Azure storage. Sitting in front of, again, we have a load balancer sitting in front of all of our storage infrastructure. There's a REST API to all of these, in addition to .NET libraries, which I think Jared will go into a little bit more. But we have blobs, queues, and tables. There's also this notion of drives as well, which is an NTFS drive system, which is really built on top of blobs. It's an abstraction on top of blobs. So what's different about these? HTTP requests come in. Blobs are ideal infrastructure for tearing apart a large image or a large video. We have our drives, tables, and queues. And blobs are really just a very simple interface for storing name files along with the metadata. There's a certain amount of metadata you can store with blobs, and Jared actually will go into some more detail on blobs. Drives are durable NTFS volumes. The beauty of the drives is that if you write to them, if an individual worker writes to them, all the writes are backed up to durable storage. So if the worker fails, when another one comes back, you can actually immediately bring that state back from the drive. Tables are not relational tables, they're entity-based tables, but they're very similar to Bigtable if you're familiar with that abstraction. But it gives you the ability to store large numbers of data, large amount of data in these tables, and actually index them over the properties. And queues are, again, reliable messaging infrastructure. And again, there's .NET and RESTful interfaces. I think I've already said that. And data can be accessed either by our Windows Azure apps or by external parties. What's nice about that is you can actually cook data products on a regular basis, where the request comes in, a data set comes in, you can have your worker rows actually process the data and then put it back in a blob, put it back into a table. Other applications which are not running on Azure can actually access them through the REST interface to pull down that data independently of going through Azure. And then the development environment. You have a complete simulated development environment on your machine, on your workstation, such that you actually look like you're writing to a blob. It looks like you're writing to a table or a queue. You can compile your application, build your workers, build your web roles, and actually test your application locally, and then press the deploy button that actually will move it to a cloud, into a staging area where you can test it out. And then finally, when you're ready for it to go live, you can say, go ahead and make this web service, make this cloud service live. So you say, what's the value add? What really is Azure adding to actually make all this? Of course, I've partitioned my data. I have this, I've put it into workers, I've put it into web roles. What really is it adding for me? Well, the whole idea is that the value add, it's intended to be a platform that's scalable and available. Services are always running. We have to expect that there's going to be rolling upgrades and downgrades over time. I mean, this service is intended to run all throughout the year. You may want to upgrade a portion of it. There could be faults that could happen. And failure of any node as expected state has to be replicated. And services can grow very large, so we have to have some way of efficiently managing all of that state. So one of the things that we introduced in the Fabric Controller, and it's going to generalize over time, where you tell the Fabric Controller exactly what do you need, what is my SLA, and the Fabric Controller is going to use the hardware available to it to actually deploy your application. So I think I've actually said most of this except the following. Again, it's a highly available Paxos cluster, but one of the things you can actually specify is fault domains. You can say, look, I realize this data center is large. My service can't afford any failures. I actually want to put them on independent fault domains, which means I want you to push my instances of my worker roles and my web roles on orthogonal pieces of the hardware throughout the data center. Different power supplies, different network, different clusters, everything. And you can specify exactly how many fault domains that you want. And again, fault domains, it's a function of compute node, a rack of machines. And when Azure is looking for how to deploy your service and even manage it over time as the system is running, it will instantiate it on different pieces of the hardware throughout the data center. So again, we could say I want 10 front ends, 10 web roles across 2 fault domains. You can be guaranteed that they're going to be on different isolated sections of the data center. Similarly, we could say update domains. This is something this is a service I expect to update throughout its lifetime, but I can't afford to bring my whole service down. And in fact, I may need to have an old copy running throughout the entire year or during a certain period of time while the new service is being deployed, tested, and even used by new users coming in. So you can specify how many update domains you want as well. This is orthogonal and complementary to default domains. And what this means is that if you specify I wanted to have two update domains, and then you actually come by later and actually push in a new instance of your service, Azure will wait until all the behaviors, all the activities quest on one sense, stand up a new instance of your service on a new update domain, routing new traffic, new requests to this new instantiation of the domain, and wait until all the other behavior on the other domain, the first update domain, is quiet before actually go ahead and continuing to roll out the upgrade across all the domains. So again, it's giving you a lot of built-in functionality for how you manage your service, how you hide faults, and how you isolate yourself from both updates and failures that might occur over time. And I think this was just a long-winded explanation for how it does that and how it combines all that, all those requests. And again, we can expect to see more SLAs that you can say when you deploy your service, the kind of behavior you want, perhaps even the ability to co-locate nodes under the same rack or within the same reachability distance for performance, but that's not quite there yet. Okay. And again, the Fabric controller, because it has an agent installed and everything, it's actually monitoring the health. Some of that health is actually the hardware. Is the network switch working properly? Is the router and the load balancer working properly? If it starts to detect that the operating envelope, the operating parameters are moving out of the envelope of normal, it will actually start to actively migrate your services off of the system. So if it detects the role has died, or if it's unhealthy, it can actually reboot your VM, your worker role, and restart your code. If it actually detects the hardware is unhealthy, it will actually take it out of the whole array, out of the fabric, and move and restart your service on a different piece of the data center. And if a failed node can't be recovered, it migrates it to a completely different part of the data center. Now, FYI, something that they're working on is basically the ability to deploy any VM up on Azure and a wire protocol for how to actually write an agent so you can actually report back to the Fabric controller the health of your VM, and it will actually manage it for you as well. So some key takeaways from this first part. Cloud services do have some specific design considerations: always on, distributed state, large scale, fault tolerance. And just because you have a data center backing you up does not mean your application is going to automatically scale. So what Azure is trying to provide in the form of these worker roles, web roles, and the role of the Fabric controller is a way for your application to automatically scale and for the Fabric controller to move around or take steps necessary on your behalf to ensure that you have a highly available service along with replicated state so it can restart from failures for you automatically. And again, it manages both your services and the underlying services as well, servers as well, to mask failures from that. So with that, I'm going to turn it over to Jared to actually show you what we've been doing for building research services on top of Azure.
All right, no problem. So what we're going to do at this point is actually move away from a kind of general description of the way Azure works and actually jump into some ways which we've made it work in the past. We've got 4 applications which we've put together either in our group with Roger or actually in collaboration with some other groups, either here at Microsoft, like the scientific group and external research, as well as some outside collaborators at the University of Washington and some other places. The first 2 we'll show demonstrations for. And after we show the demonstrations, I'll talk a little bit about how the second 2 work. And then we'll kind of, from there, once you get a sense of what Azure can do, I'll describe how we put those together. And hopefully with that context in mind, we can then move on to taking a little bit of a deeper dive into how the Azure works. So if you wanted to try it yourself, you might have kind of a background in how the technology works together. So I'm going to jump out of PowerPoint at this point and move over to a demo. Right here. This is Azure Blast. Not everyone here is a biologist. I realize that. I'm not a biologist either. It's amazing how much biology I've had to learn at Microsoft Research. It's not something I expected. But the Blast program is something we didn't write. It's been around for a long time. It's a very well accepted algorithm for taking input sequences, whether they're proteins or DNA or whatever they might happen to be, and then comparing that against a database of known sequences. And it returns what it thinks are the most relevant hits. And it's not like a regular database lookup. It has to do a lot of little things like what would happen if you inserted a few characters here or took a few away here. So it's a pretty involved algorithm, and it's definitely the standard that's used out there. So we thought to ourselves, well, as the science gets larger and larger and people are trying to compare more and more things, wouldn't it be great if we could just take this application which already exists and distribute it on a lot of different nodes? And that's what we've done. So this is a web interface. It's a web role on Azure. Basically, you go and you select an input file of some sort. In this case, it's a FASTA file. FASTA is a very common format for representing either DNA or protein sequences. In this case, these are DNA sequences. There's 10 of them in this file. That's why it's called Sudan 10. So I just tell it to look into that. BLASTP actually looks up proteins. BLASTN looks up DNA. BLASTX will look at both. So I'm going to switch that to BLASTX. That's what we're going to run. There's only 10 input sequences here, so it doesn't really make that much sense to use 25 computers to figure out what those are in. So I'm going to take that down just to 5. And I can also select which database I might happen to want to use over here. And I'm just going to point it to that. I think here that's the only one that we have available. I've actually also in this, you don't have to do this, but what we've done here, we've also allowed you to log in using your live ID so that you can submit multiple of these jobs. Some of these jobs may take a long time, but you can then go back and look just for your jobs and see what the status is of them. I've already logged in. And I will call this our Cloud Futures run. So that's all the parameters we need. And basically, I'm just going to hit submit. And what this is going to do is it's going to take from the web role, it's going to take a message and put it in one of these Azure queues, which Roger talked about. It says at the bottom there, the request was submitted successfully. I can now quickly, this is not a long-running job, so I can look at the jobs that are out there. Here's the status. There's some that have been completed. This one's currently running. I can go look at what's happening to this particular job. It's telling me that it has broken it up, that split the sequences into little tasks, and several of them are up and running right now, and it hasn't completed yet. And it's actually refreshing in real time there. And eventually, it will end up just like any of these other jobs which have already completed here. In fact, there it says it's already succeeded. This was a very small input sample. And it's now telling me up at the top here that it did get a result. It's just in a URL. It took the result of what BLAST would have given you normally had you submitted this little 10 input file to it. And it stored it up in a blob up in Azure. And this is the URL which requests that particular blob. So I could, if I wanted to, just copy this URL, paste it back up into my browser, and you get what you'd expect. I said the output should be in XML, and that's what I got. Not all that interesting in this particular run, because you could have done this very easily with NCBI or EBI, which are the public and free available versions of this. But imagine we had something come up just 3 weeks ago or so, where we were working with a SAGE group. That's a bio group at the University of Washington, and they had just sequenced a new bacteria. They didn't know much about it. They had 700,000 sequences that came out of their sequencing machine. And they had actually tried. They went to NCBI and they tried to submit this job up there. And NCBI, every time they did it, after a few hours, kicked them off because they were blocking off everybody else who wanted to use the service. There was no way that they could get this done, and they had this deadline for getting it done. And so they heard about us and they came to us and said, well, can you do this for us? And we were able to do that. We were able to take their input, spread it out across 50 nodes in this case, and get that done in overnight, basically, when it was something that couldn't be done before. And they had a 1-week paper deadline, and they met it. So we were very proud of that. Let's get back to the PowerPoint. So that's one. That's kind of very typical way, right? You have a web role, has a web interface which gets to a worker role, does the work for your reports back using the data storage. A whole different way is something we did also in conjunction, not with the University of Washington, but not with their biology side, but with their oceanographics. You saw, hopefully, Ed Lazowska's talk earlier. This actually came from work that one of his students is doing. This is Cove. It's like a virtual Earth. It's like Google Maps, only it doesn't go on the land. It goes underneath the ocean. So you take all the data that may come along from that guy in the rowboat sticking his head in the water. You bring that up here, put it in their formats, and it'll visualize it. What we've done is we just added a little bit of a service. It's almost transparent that Azure is working here. But what we're saying is that there may be some sort of data product you need to compute, and your computer might not be sufficient for doing that. It's great for visualizing and displaying the results of it, but it may be something that needs to happen over a much larger run with a lot more compute resources. So we have a back-end service that we've written on top of Azure. We call it Anthill. And what it does is it allows you to submit compute jobs to it. You can look at your whole history. This is all of the runs we've ever done in various jobs. If you wanted to start a new one, what it's basically doing here is listing all of the algorithms that it has and that it knows to do on the data that's available. I could pick, I want to do advect particles. Again, I'm not an oceanographer either. I'm not sure what advect particles does, but it's a job that runs in a reasonable amount of time. Once I've said I want to run this job, it tells me what nodes it knows are available. I can select one, or I can just say use whatever's available, and it will go off and the job is started. And again, you can track the status, or you can actually look at jobs that have already been completed. So if I go back to this one, there's the one I just launched. There's one that's already been completed. I won't wait for this one to complete. But the other thing it does is it registers the data products that come out of that particular job. There may be more than one. In this case, there's only one. You can select that data product, say this is the one I want to see. It will download it back from that source on the web, and then Cove visualizes it. My UI is not closing. There it goes. So that's the visualization of it. It turns out that it's much better to have your computer with its graphics card doing the visualization. It's much better to have something where there's intense computation happening up in the cloud, and that this marries the two technologies pretty well. All right, back to the PowerPoint. Another project that I didn't personally work on at all, but has been very interesting, is the Azure Modus project. And this project is one where there's some satellites that have been, some government satellites put up, I believe by NASA, that are taking visual imagery of the Earth as it's passing by. And what it's trying to do then is to stitch all of that data together, hundreds and thousands of these very high density photographs with different angles and different conditions at the time when there's snapshot with the atmosphere and things like that. So it has to go through several iterations of computation on these images. You've got all these various different computers are bringing down the data. It goes through collection, reprojection, derivation, analysis, until it comes up with something that makes sense to that particular scientist. And again, it's got a web-based front end, and I don't know what these results happen to mean, but it's a way of taking something that's very intense computation and bringing it to the scientists without them having to worry too much. PhyloD, another biological example. This comes out of David Heckerman's work. This is probably the first application which we worked on. This is well before Azure was even released. It was just in its early stages. But it concerns HIV vaccinations and AIDS. It turns out AIDS mutates very heavily, even inside a single instance of a host. And because of that, it's very difficult actually to come up with a vaccine, because the vaccine actually targets on particular proteins that are generated inside the HIV. Well, most of them are generating different ones, even inside one person. So what they do is they take what they call phylogenetic trees, which come out of the way that the AIDS virus mutates. They track that, and they have to do an analysis which sees which are the most common, which of those AIDS viruses are fragile, which are not. And what this does is it took a job. A lot of these jobs are between 10 and 20 CPU hours, but the big ones were around 1,000 to 2,000 CPU hours, and it was able to reduce it in an almost linear fashion so you could get the results almost right away. All right. And yeah, and this image on the right was actually featured on PLOS, which is in the biology world is big. So let's talk about how these work. Azure Blast is staged. You have a worker role, and this is a very typical pattern inside of Azure. It's basically you have an initialization function. Anyway, you have a step where the program is deployed, and basically what that does is it takes a large database, the database which you're trying to search on in the Blast case. It compresses it down, sends it up to the storage fabric that's up in Azure, and then each one of the workers which is available for you to run on takes the compressed data and puts it locally onto its own onto that particular worker role. And what we use is we didn't rewrite the Blast program. We take the one that's actually used in NCBI, EBI, the one that the scientists trust, and we copy that as well. So then the user comes along with their input, sends it off to a web role. That web role partitions it out into acceptable little tasks that each one of the worker roles can work with. Those tasks, as they're partitioned apart, put a message on the queue, which Roger talked about, and all the workers then take those messages off the queue, do the work, take the output, write it back up to a blob on there. Now this particular result, this is just a lot of dots until you kind of understand what's going on here. We actually just did a project where we took 10 million sequences. There's a kind of the latest non-redundant protein database that's up at NCBI. It has 10 million sequences inside of it. And what we wanted to do is take those 10 million one at a time and search one at a time against the entire database. So basically you're looking for the things that are most like that, and you can find the clustering that's involved. So that's a huge job. We figured when we did a few computations on it and a few test runs, and we figured it would be a little over 10 years if you did it on one computer with 8 nodes. And what you're looking at here is, in order for us to do it, we couldn't even fit it in one data center, actually, the way the allocations worked out with Azure. We had to spread it across a few data centers. What you're looking at here is 1/3 of the jobs in one of the data centers. This is about 1/8 of the work. Inside of here, these are the rows here are the computers we ran on. So we had just over 60. We had 62 in each one of the clusters. And this is each task being completed. So this is a partition, a small set up to 35 of the sequences at a time happening in a run. Now, the interesting thing we found about this, these red points are where we had failures. And we expected that. From time to time something would go wrong. And fortunately, Azure just kind of picked up. You see that the machines don't stop. There are blue dots after the red dot comes along. And Azure's Fabric just did that for us. And it just picked up from where it went. We only had to rerun where these red dots were. But the interesting thing to us was that it was going along, and these were working out. See how dense this is through here? It's running quite quickly. The partitions don't change at all, but you actually see that it starts spreading out a little bit more. And then towards the end, it starts getting dense again. So there are just conditions that are out there. We don't know what this is necessarily due to. It may be that the data fabric itself is being used more heavily by other processes. It may be that some sort of updates were being pushed through. But all in all, it's still good results. More interesting is what we found in one of the other data centers. Now you can see that was very similar from about here over to the one that we saw before. It's probably even a little more even. But what happened here? What we saw was that every single one of our computers at some point during this day in the morning failed and then came back. And then something else happened. I think that the data center may have caught on to something, or an update was happening, and they decided to shut all of our computers down at one time. So you see this vertical line where everything shut down. The nice thing is that it all recovered from that, but it does show you that there are external conditions out there that you just can't even plan for. The power may have gone out at the center, or some critical system update may have happened. And then we still haven't figured this out either, but some of our very last jobs took more than a day to complete. And that may be something inside of our software. We're still actually just running this. These results came off last week, so we're not even entirely sure. We're still analyzing it. Anyway, some lessons that we learned in working with these large data sets is that no matter what system you're working with, I think you have to always plan for failure. And that failure can happen at any time. It can happen while you're deploying. It can happen in the middle of a run. It can happen while you're writing the output to the store. And you have to, in order to be able to accommodate that failure, you have to both be able to listen to the logging messages that come back from the fabric, but you also have to be logging yourself so that you know where those are and where you need to focus your attention when the job is done. Test runs are your friend. This last computation we did was probably over $20,000. And we ran a few test runs on very small sets of the data, and we found lots of problems with our first theory of how we should run it. And so if those little test runs cost us $100, I think we're saving ourselves quite a bit if we don't have to run it 3 times at 20,000. All right. But the great thing is that Azure or whatever cloud technology you happen to be using is a really good thing. It's something where you can get a lot of your work done in a lot faster time. This is like Azure PhiloD actually showed these results. It basically, as you increase the number of instances, you decrease the clock time pretty much linearly to a certain point, at which point you peg out. So there's an optimal amount of computers you can run at it. With Azure, we actually found it that basically if you got 100 computers that you added to your runtime, you got a 94 times speed up. So you're getting close to linear speed up. All right. I did want to also point out not just how Azure worked, but that Azure Ocean project which we're working with. It operates on a much different principle, a much different pattern. In this case, what we're actually doing is we're using a registered type system where you say that you have some sort of computation, and it doesn't have to fit any particular model other than to say that this has to work on some sort of data to produce some sort of data, and you can register that up into a central database. And so the jobs themselves, the computation, and the data that all comes out of it goes and gets registered into a central database. You can then apply this technology to any type of application which you feel like you're prepared to write. All right, let's just, I'm probably taking up a lot of time, so what I'm going to do is talk a little bit more about the fundamentals of what is involved in Azure. For those people who are we've talked about this already, Roger brought it up, there are 3 fundamental types of data inside of Azure. There are queues, there are tables, and there are blobs. On top of that, on top of blobs, there are drives. And on top of this, and kind of external to this talk which we have, which we didn't have time to go into, is also the SQL Azure stores. So you can actually get a relational database and work it in Azure as well. Each one of these are accessible through very, very well-known patterns. You can use REST by just doing HTTP, or a secure HTTPS. You can use .NET APIs to get at them, or you can use something more like an NTFS drive. When you create an Azure account, you basically sign in with an ID that identifies it to yourself, and then you have the flexibility to choose also where you want your services to run. And that's based on the data center and what we call geocenters. So you can say you may want it to run in the United States, or for some reason or other you prefer the European servers or the Asia servers. You can choose those things. Once you've done that, you can actually choose to have both compute accounts and storage accounts. And your capacity is tied to your account, but you have up to 100 terabytes per storage account. And you have, when you first sign up, you have a limit of 5 storage accounts. So that gives you 500 terabytes of data, and you can request more, but kind of like we saw earlier, if you want to request more than that, they're going to make sure that they're going to contact you to make sure that you're really going to use that. Otherwise, they don't want to get over provisioned. So how does this work? If you have a blob, if you want to write some data, you have an account. Inside of your account, you can create as many containers as you want to, so long as it stays within the amount of data. You have that 100 terabytes. As long as you don't exceed that, you can have as many containers as you want to. Inside of those containers, you can have as many blobs as you want to. And each one of those has a unique ID. They have a name which is readily accessible through a REST API. So if I had this picture 1 that I wanted to access, all I'd have to do is type in the account name .blob.core.windows.net / the container name slash the blob name. Now there's no multiple levels of containers. You can't have a container which contains a container. But the interesting thing is that blobs inside of Azure actually allow you to have the slash in their name. So you can kind of fake it to have multiple containers by saying my blob is called my family slash pick one or something like that. So it would look like in the URL that that there's more structure than that, but there is just one level of containers. Each blob container holds a set of blobs, obviously, we talked about that. And the other important information is that you can associate metadata with every single blob. You can associate metadata with your account, with the containers, and with the blob. So if you want to do name-value pairs to say if it's a picture, what's in that picture, you're perfectly welcome to do that. The limit is that you can only have 8 kilobytes worth of storage. So what most people tend to do is say, this picture has information about it, but I've stored that up in an Azure table. Go look at this table and this entry. And that's about enough information in 8 kilobytes to do that. There are 2 types of blobs. There's the block blob. This is targeted for streaming reads and writes. And it has a limit of 200 gigabytes. There's also a page blob, which is actually somewhat new. And it's more for the random read-write scenario. It has a bigger limitation, 1 terabyte. So really there is one more level of abstraction, but you can't get that from any of the REST APIs. You actually break down the blobs into smaller chunks if you want to. But when somebody goes to download them, you just get the whole blob. So let's illustrate how this might happen to work. Say you have a 10 gigabyte movie which you're wanting to put up on Azure. You create a blob. We'll call it the blob.movie. Maybe it's that movie or whatever on there. And then you have all these blocks. And one by one, you put those blocks down into your blob until you've reached the end and you've put all of your blocks down. Now at this particular point, your blob hasn't actually been created. All the data is up in Azure right now, but it's just a bunch of little chunks and nobody could access your blob. There's just a placeholder there. What you then do is you say, okay, now from all those blocks that I've put up, put the whole thing together and then make it accessible. Now why did they do that? Well, the reason is that in a lot of cases, if you have a very large data set, especially in the scientific world, that's coming from a lot of computation, which you've done across a lot of different nodes. By doing it in this format, you can actually have all those different computation nodes sending up this data all at once. And then you can have a check done to see if some of those were failures and whether you wanted to skip them or not, or whether you wanted to have them redone, and you didn't have to do it in just a sequential format. So it's actually quite useful for being efficient in cases of failure and for getting things done out of order. So here's some details about that. I'll let you go back and refer to those later. Page blobs, on the other hand, have a larger limit. You actually say what size you want your page blob to be, and it allocates that. Now, where the block blobs, actually each block could be of a variable size, the pages themselves actually are of a fixed size. And then you read and write to it at whatever random sequence you want to. So here we go. Maybe the first thing we wanted to do is write in those few pages. And then if you wanted to write again, you got the other data, and you saw it overlapped. Where that was, it wrote right over the pages that you had started from before. You can clear those out and keep going until you have the data which you're looking for. Now, once all those operations are done, you might be asking, okay, what part of my data is actually valid where I've written to? You can actually query against the .NET APIs, get the ranges which are valid, and then go and ask for the data in certain ranges. So what you'll find, and the most interesting aspect of this was that they've actually mapped an NTF file system. So on your worker roles, you can allocate this page blob, and then you can say each one of these particular chunks happen to represent files. Well, each one of the blobs and the different sizes and different offsets might represent different starts of different files, but now you've got a way of overriding those, putting them in different places, having it always redundant, backed up and replicated and ready to go at any point. Anyway, all right. So since you've got those 2 different types of blobs, you need to know when to use which one, and that is normally it's your access to it, whether you want it to be streaming whether you want it reading, writing, whether you want to use it inside of a drive in your worker roles, etc. Now, snapshots is another interesting aspect. And this is just something provided by this data storage fabric as well. So if you happen to have a blob out there and you want to make little changes to it, but you're not sure that those changes are something you want to commit to, you can actually take snapshots of your data. So a snapshot is like you would expect with a snapshot, a picture. It's like taking a picture of the data and putting it over here and having a copy, and it's just pointing back to that other one. But the nice thing is now you have different copies you can work with, and you're not actually paying for the extra data. You're just paying for that one set of data where it's actually being stored. And then you can try and put different blocks on top of that. So in this case, I take a snapshot of my original data, and I try changing something in the middle of it, or I try appending onto the end of it. I can keep going like that until I say, oh yeah, that's basically what I want to do, and then I take another snapshot of that. Now, basically, I've got 3 sections of data here, but I'm only really paying for the blocks which are unique. And then with the second snapshot, I can do the same thing. I can add on to it and say, in the end, that's the one that I really did want after all, and promote that to being the original blob. So this is actually a very handy function for when you're having to work with data that's going to change and still want to be able to go back, have a history. All right, Azure Drive. This is we're finding this in scientific applications is actually a very handy function as well. For instance, when we were working with the BLAST application, we didn't change the BLAST application at all. Well, it doesn't have any knowledge whatsoever of what Azure blobs are to get its data from, but it does know how to work with the file system. So if you can map the blobs that are in your storage already in Azure Storage Fabric into something that looks like the file system, then you can use legacy applications you may have written in Fortran, you may have written in Perl, you may have written in Python. Anything you want to that can run on a Windows Server system can now access a file system in the background, actually be hooking up to Azure storage. Azure also provides a big table implementation. So this is the second type, the blobs and then tables, and then we have queues. Basically, it is just a way of writing up key value pairs where there's a partition key and there's a row key, and these are the only things that are indexed. It actually does very quick lookups based on those keys on the partition in the row, but if you wanted to do something more complicated like a SQL statement, which is doing complicated joins on tables or things like that, you'll find that it's not very efficient. The data model is set up to record entities on partitions and rows. All right. So the very last thing I wanted to show you is that we have been, as a group, looking at a lot of different best practices. We've been measuring things, benchmarks, what are the performance like. If I have an application that wants to run against a data set with a lot of partitions and it's always accessing the same blob, every worker is accessing the same blob, how many workers can I have accessing that blob at one time? That's a question you may want to ask. We've been trying to answer that by measuring those exact data. And we've put together a list of things which would be useful. So if you do decide to come and give Azure a try, you may want to come take a look at these best practices, as well as, once you've looked through that, take a look at a couple of websites which we've put up. The first is a website to our particular group. It has a lot of interesting pointers to resources in terms of learning what Azure is about, some presentations, some samples, some scenarios. And the second one has our benchmarks as well as a lot of the best practices we've learned. Things that we really wish we would have known when we started doing the development. And hopefully will be helpful to you as well. All right, with that, I'll go back to Roger.
Thanks, Jared. I'm going to go back to Jared's slide just for a second. This has only been released very recently, which is our Azure Scope, which is in fact a benchmark suite. I mean, Jared has covered a lot of information here on Azure. As you can imagine, a platform that you're not familiar with, if you're thinking about how to port your application to it, you're going to have a lot of questions. So this is something we've actually built the Azure Scope benchmark suite, which has micro benchmarks and end-to-end benchmarks. We actually pulled some of our friends in the community asking for their best practices, their advice on benchmarks. We've added it to the suite. And we'd certainly welcome your feedback on new benchmarks to add. And we're going to be rolling this benchmark out across our different data centers, because in fact the different data centers, given how fast this technology is moving, run differently. So you can ask, if I'm running at this data center, what can I expect for performance? And the best practices that Jared summarized there is just a sample of what we have on the site many of which are backed up by actual benchmarks to help you craft your application. So I'm going to close the talk out by talking about our cloud research engagement, because I started by saying, the role of our team is to support researchers in leveraging the cloud to support their research, and that's kind of a vague statement and broad. So I'll tell you a little bit about what my team does. And so, yes, we are building the services that we've shown you. We're releasing them as open source, and we think this is just the start of the tools that we're going to be building, providing to researchers to leverage the cloud. Members of the team, and this is really part of an international engagement program where we're offering cloud resources, access to Azure over the next several years to researchers and academic communities. And we're backing up this offering with a technical team, our team, to actually help researchers get their applications up and running on Azure so that they can be successful. And we're really trying to articulate as a community what research workloads, what applications run well on the clouds, what should really be staying on the cluster, because as a community there's still a lot of open questions, and it's going to vary from community to community. So we're looking for partners to actually explore this. And part of our charter is to lower the barrier to entry. There's a lot of unknowns about moving to the cloud, so what as a team can we do to provide tutorials, code accelerators, best practices, and our team is actively involved in trying to support policy change. Today with NSF, it's easier to get 200,000 or $500,000 to buy a cluster as opposed to buying time on a cloud, so how can we affect policy change? And we've got a lot of work to do inside the company. If you had a chance to listen to Deepak's talk today, researchers can send into Amazon data sets that they like to have uploaded. So we have to educate our own company on what kind of services we need to provide as a company to make our cloud useful to researchers. Because if we had a longer conversation over a drink tonight, research workloads and web services that .NET and Azure is targeted for are not necessarily mutually cohabitable. You have to actually move one and the other together. Data sets. We are going to provide select reference data sets on Azure. Data on the cloud is a lot like free puppies. You have to maintain it and support it. So we're waiting for community pull. And so what we're really trying to do is look for communities that would say, yes, if this data set was available, it would actually catalyze a community, so it's worth our investment if people would actually use the data to support their research. But what we are focusing on right now, where we are making an investment, are tools that we can give you to get your data up into the cloud seamlessly from clients to help you upload data from client to cloud. And then later we can talk about what reference data sets make sense for a community. And services. We're just starting to touch the surface, and we're starting to reach out to external collaborators to say, what services should we stand up that would make a community much more empowered to solve problems. I'll talk about that in a second. And we're really asking the questions, at what point can we build enough services, put enough research data, enough accelerators that we can stand back and the community will take it and go forward from there? What does it take to catalyze the community? We don't want to continue to make investments, and the day we stop working with the community, the activity stops. Just what point do we have to push it till the community can take it to the next level? And we're also asking ourselves, what products in Microsoft should we make cloud friendly for researchers to use? Which helps me transition into the next thing. This is something Ed talked about in his keynote this morning, the Branscombe pyramid, and the text kind of got messed up on it. If you look at the research community as a pyramid, at the very top of the pyramid, you have people who have supercomputers. They're not going to be needing any access to the cloud. And at the second level of the pyramid, you have people that have clusters, they have support teams, and again, they are well prepared to carry out large research at scale. But the rest of us who don't have access to this kind of capability, how can you make them just as empowered to carry out research, even if it's just for a few days? And so that's really what our focus is. And in fact, this community, we say, they use laptops, a lot of them. They have, small desktop workstations. They're collecting data at furious rates. Now, what can they do with it? What kind of tools can we offer them in the cloud to actually analyze and do something interesting with that data? And it's really about analyzing the data. It's not about flops or how fast this runs relative to a cluster. It's about how fast can they get their research done and not spend as much time as they are currently spending writing software. And we think that this could represent a paradigm shift for research for two reasons. One is, yes, you do give people the ability to actually, as Dave Patterson talked in his talk today, of having this surge capability for those brief periods of time when they need more than the cluster down the hall, they can in fact have access to that capability. but it also actually broadens participation. You have so many groups that we talk to, university groups we talk to, that simply don't have large clusters and capabilities. And again, like the work with Sage that Jared told you about earlier, for those brief few days, they actually, the group that we worked with had hundreds of nodes they could do compute with. The total cost for the bill was $200, and they got a publication. They won't need a cluster or a blast service for a lot, for months. So how can you actually give them tools to carry out research like that? And again, have funding agencies fund those kind of workloads versus making them justify the expense for buying a cluster, which they may or may not get. Our take on this is that we're looking at how to use the cloud as an intellectual amplifier from clients and tools that researchers are already using, which is why we like the Cove example, because again, it's a tool that the community built. How can we actually make the cloud invisible to that, where they're actually just using the client, specifying some research, and the work gets done. And of course, one of the best tools we have is Excel, and as we heard in Ed's talk earlier today, the sheer volume of data, both in business and science, it starts with Excel. How can we actually amplify that with the power of the cloud? So we're looking at research add-ins that can actually move the data from Excel up to the cloud and actually show you libraries of functions that you can run against that data up in the cloud. So again, the cloud in its presence is really invisible except for the capability it offers to the user. And we really don't want the user to have to think about whether they're running MapReduce libraries in the back end or they're invoking R or MATLAB scripts. All they see is buttons that represent the kind of analysis they want to perform over the data. And in fact, they may be manipulating a petabyte of data, but they have just some window that they're actually viewing that data with on Excel. And our team is looking at, well, how could we provide data visualization capabilities? How could we provide provenance so that if you did cook the data and you did bring it back to your client, we can explain how that data got created, and how can then you actually have collaboration spaces in the cloud so you could publish that data so others could then analyze it and share your insights with you. We also have our engagement program. So we recently announced, and the call for proposals is currently out with the NSF. We're offering the NSF substantial access to Windows Azure. NSF gets to choose the projects and complement it with NSF funding for the researchers to use the cloud for their research. And we'll be doing this for the next 3 years. And they have access to our team, and they also have first-class support from Azure should their service fall over and they need to have some technical support on Azure. Our current offering, and that probably will grow over time because as the costs fall, is 20 million core hours per year, 200 terabytes of triply replicated storage, per project, 1 terabyte per day per project of ingress or egress. And again, that can change over time. In Tier 1 support for Azure. And this is an international program. This is simply what we're offering here within the US. It's an international program. Discussions are underway in Europe and Asia. We're not ready to make any announcements yet, but this is intended to have similar engagements in other countries through government agencies, letting them choose. But what we hope to see from this on our website, which I'll show you, Jared had the URL earlier, is we're starting to write up the use cases. What did people use Azure for the research? Where's the code? How can you download it? How can you build on what people have already built? And we are right now rounding up tutorials and information, programming guides, etc. on Windows Azure. So we have a separate page on that if you go to our website. The benchmark suite is also available off this site. Tools and services, which is code that we're writing, both the source and the service if you want to stand it up to use in your research project. And frequently asked questions, which are common questions people ask when they first come up to Azure and are trying to understand how to leverage it for their research. And again, over time, code accelerators, tutorials, programming samples, etc., that we're going to use to help support the community as well. So this is what we hope to be our community presence and help support researchers as they're starting to dabble with Azure. And of course, there's also an email alias that you can send us email. And if it's a great question, we're actually going to not only provide the answer, but the code that we might have used to help solve the answer and put that up in the facts so the community can see what other people are asking about it as well. So that's pretty much all we wanted to cover in our tutorial other than answer your questions.
So I have a mic floating around, so if you have a question, please raise your hand and I'll bring it to you.
Bertram?
Maybe I can shout. Just a small question. Would you care to compare the Azure tables with the big tables that were presented in the Google talk earlier this afternoon?
Birds of a feather. Okay. Very similar. I mean, yeah.
Hi there. Did I pick it up right that it's possible to run native libraries on these Azure nodes? More of a prosaic question.
Yes. Yes, it is. It supports both managed and unmanaged code, yes, and so you can actually run native libraries. And soon you'll have the ability, and this was announced at Mix, that you'll have the ability, soon Azure will be running Windows 2008 VMs. You'll be able to actually download the VM to your local machine, image it yourself, and push the differencing disk with all the code you've installed, everything that you've baked yourself, push the differencing VM up to Azure, and it will manage that for you, so you can pretty much install whatever you want as a worker node VM that it will stand up.
Hi. In a science context, supposing that someone uploaded several blobs with raw data, is there a model for sharing these blobs between different applications instead of using the standard APIs, a more efficient way?
Thinking drives and snapshots, or go ahead, Jared.
So I don't know how clearly we made this, but there are both storage accounts, and let me know if I'm not answering your question. There are both storage accounts, and then there are your compute accounts. Your worker nodes and your web roles come off of your compute account, and then you have your storage account where you're storing all of your blobs. Now, all of your worker nodes have access to any of your blobs on the other account. So by their very nature, they are actually very much accessible. You can also set a flag on them as to whether they're public or private. If they're private, then basically only your worker nodes and your web roles can get at that particular data. If they're public, however, then anybody with a web browser can point a URI at it. It's at the blob level, although you can actually set the bit for public or private at the container level as well.
Yep.
Any more?
Please.
Is there any educational program to introduce Azure in the curriculum and that the students can access the small number of nodes?
So the question was, if I got it correctly, is there any plans or any preparations for providing Azure for academia so that the students can actually experiment with it and use it? Our academic outreach team is working aggressively to make that available. They already have different offerings, and I know there's people here we can put you in contact with, but they're trying to even streamline that process to simplify how academics can actually get Azure to use in their classrooms for students. Jim, do you have something you can add for that?
Krishna can talk about the session.
Krishna? Okay, very good. Krishna has a talk tomorrow, but he's also identified himself. He's the session chair, so you can actually tag him or come to his talk tomorrow and he can talk to you about that.
Yeah, so tomorrow at 2:30 to 4 is the academic Azure focus session. So yes, we will address some of those questions there. And also, we'll be announcing tomorrow morning that everybody here will be getting an access token for Azure that's good for a month, so that you can basically take it and test drive it, basically. And in tomorrow's session, actually, we'll walk through step by step, in terms of setting it up and all of that. So a little plug, so thank you for that. But absolutely. So the question was, what does the token mean? Basically, it's a username and a password that we've set up for everyone here that allows you to log into Azure and get access to compute and storage. On compute, you get 20 instances, basically, which is the exact same account that you get when you sign in with a credit card as well. Storage are the same accounts that they mentioned there. You get 5 storage accounts and 100 terabytes per storage account. So the exact same ones. Thank you. Hopefully, the question was, is it only for 1 month? Can we not go beyond that? And I guess that sort of falls back to what Roger mentioned. We're basically working on a strategy. This is, if you will, a sort of a way to test drive it. And we'll hopefully have a sort of a segue into a fuller, longer-term plan. And so we'll, again, talk about, I don't want to take away a lot of Q&A time here. No. We'll talk about it in our session tomorrow evening.
You can be guaranteed a lot of people really care a lot about making that happen, so we'll work on it.
Can I follow up real quick, too, on about the native code putting in? In the existing way that Azure works, there's a managed API for basically when you say your worker's ready to start. It gives you just one little function, the start method that you have to start with. And the way that we've done it, and the way that I think is very common in the science applications, if you've got a Fortran program you want to distribute, or you got a script of some sort you want to distribute, is you bring that up into Azure in the storage account. And then when your worker node starts, it goes and copies it from that storage account, takes that executable, sticks it right there on that worker role, and it just let it go from there. Just say start, and whatever you've written before, native or not, will be working. It's a very easy pattern.
Yeah.
Could you comment on the optimizations that you did for the? Oh, sorry, I didn't catch it.
We'll have to get the microphone over to you.
Oh, please go ahead. Sorry.
Yeah, real quick question. We didn't talk about SQL Azure, but with SQL Azure, is analysis services a component of SQL Azure? What's the difference between SQL Azure and SQL Server? I mean, what are the BI capabilities at this point in time on the cloud?
Yeah, so BI, the short answer is SQL, the difference between SQL Azure and SQL Server right now is size and access to MasterDB. Size right now is offered in 1 gigabyte, 10 gigabyte, going to 50 gigabyte in size initially. You have no access to MasterDB. They're now adding geospatial in the next couple of months, and SQL analysis service is coming right along behind it as well. So again, they're pulling through more and more of the functionality behind SQL, and actually also building something called Dallas, which you're going to hear about tomorrow if you're able to attend, which is really a data mart, the way of discovering data, discovering other researchers' data, and being able to mash them up. But again, the functionality from SQL, Azure's new, SQL Azure's even newer, and they're pulling more and more functionality through, but it will be present.
Could you comment on how you optimized the virtual machines for your data centers? Because you mentioned it's an optimized VM, but any details available there?
The only control you have over your virtual machines is actually their size. So there are 8 cores on a virtual machine. You can request whether each of your machines has all 8 of those cores, or whether it has 4 or 2 or 1.
Yeah, but there was a question, I think a more subtle question is exactly how does it differ? How does the hypervisor differ? And so one of the key architects in the company actually built the hypervisor for Azure. Those changes are now being back propagated into the regular hypervisor that we use. They just wanted the most efficient VM they could possibly get, and also allow just fair sharing. You can't actually create a VM and say, I got 80% of the network in the disk. So they made some simplifications and optimizations, and then they benchmarked it against the regular one.
But does it provide for better performance isolation compared to other technologies, would you say?
The Hyper-V they're finding it. I think they were rating it at like 98% efficient.
Yeah.
So it's really good on.
And I've not seen a side-by-side comparison against the Azure Hyper-V and the regular Hyper-V to say exactly where the improvements were made, other than a handful of people. Dave Cutler in particular decided he wanted to actually have a more optimized hypervisor and made a call there. And again, it could be just be simplifying the stack and the footprint. I don't know. But like Jared said, the performance numbers are actually very good. The published numbers.
One thing to note too is that as you request larger nodes, the full 8, you also get more storage off of the machine, and you get a larger throughput in the bandwidth. That's one of the things we put in the best practices, which I didn't go over.
Yeah. And we're benchmarking that to show exactly what you get, networking throughput and other things as you ratchet up the size of your VM, just to prove it to ourselves. Yeah. Any more questions? Yes, please.
When Azure with .NET 4.0 will be available?
You can use .NET 4.0 right now.
Yeah.
No. Yeah.
So, if I may, so basically, .NET 4.0 is releasing 12th of April, and the direction from the Azure team was basically, they're basically saying 90 days from the date of release, but optimistically...
But I can tell you it works right now, with everything I've done.
Right, so on the cloud, 30 to 45 days. So sorry? The SDK will be updated at the same time. It's going to... Any other...
I just wanted to ask you whether there is any synchronization between what you are doing and the development of the Windows Phone software, because that's probably one of the possible clients for cloud computing in the future. So,
well, Microsoft's a very diverse company in terms of technology. We have different stacks, including the presentation layers and the communication layers. WCF is a way to access the REST services and the SOAP services, which Azure provides. Those clients will also be available are already available on our mobile platform, and will continue to be.
I wanted to ask, maybe I missed it in the presentation, is your API close to what, for instance, Amazon is offering, or has nothing in common with it? Well, if by API, I'm actually even referring to the RESTful access to your services.
Oh, so on the storage, I can speak from what our team did earlier when actually trying to make sure we could write storage to S3 or to Azure. Very, very similar. But on the computation side, with EC2, you're actually deploying VMs, managing VMs, so that gets much different. But in terms of actually provisioning storage and stuff, yes, that is very similar. Very few code changes were had to make, because we try to make our code work on both platforms. If researchers want to use S3, they can flip a bit and try to write things to S3. It gets much different when they try to go to change the compute API.
I want to make two super quick comments that are both pretty obvious. One is that Microsoft's provision of sort of technical programmer talent as part of their NSF arrangement is really unique. And it's important to scientists and it's important to all of us because there's people who can actually help people move stuff. The other thing something Dave has mentioned in a number of his talks but didn't mention today is a really obvious phrase, and that is that one computer for 1,000 hours suddenly costs the same as 1,000 computers for 1 hour. Probably vice. Did you say it? I didn't see it on your slides. Okay, I guess I wasn't listening. Anyway, that just really drives it home to me, and it's true of a number of Roger's examples. It's a remarkable transformation that you just kind of didn't think about being possible until a year ago.
Yeah, if the vice president were here, this would be a big freaking deal, right?
Okay, everyone. If there's any more questions, otherwise we'll say thank you for attending and thanks for your patience and see you at dinner.